So for the first part of the experiment, we're going to use the ITC5292 as our transmitter and the F33 as our receiver. So I'm going to go ahead and drop these into the water. And make sure with the F33 that the soft side, which is the transmitting side or the active side, is facing the other transmitter. You want to make sure that the transducer is facing your other transducer. You want them to be parallel. You don't want it to be twisted at an angle like this. Make sure that you measure the distance between the two transducers with a 2-meter stick. It's not important that they be 2 meters apart exactly. What's important is that you know the exact distance and that you keep the distance exactly the same for each measurement. To keep things simple, I measure from the center to the center of each of these poles rather than trying to get the face of the transducers. So the way I'm hooking up my transmitter to the power amplifier is with this series of banana plugs. And the purpose of this is to have a current sensing resistor in series with the transmitter. So what happens is the signal comes out of here, goes into this plug, which is just a shunt, comes across here, and then to here. This is the transmitter cable, so it runs through the transmitter, down to here, across the current sensing resistor, and then to ground. So this is the way it goes. You want to be sure to have it hooked up this way, and so that the current sensing resistor ends up at the ground of the power amplifier. And the reason is because you're going to hook up a couple of banana cables here, like this, to read the voltage drop across that resistor. And this black cable goes to a ground on whatever you're using to measure that voltage. So you want to make sure that that ground is connected to the ground of the power amplifier. If the resistor were to come first in the circuit, you would be introducing a ground into the middle of the circuit, and that would cause problems with your measurements. We'll use the oscilloscope to look at the signal that we're using to drive our transmitter and our signal from our receiver. So the top trace here, channel 1, is the signal that we're using to drive our transmitter. The reason we're using a chirp with an FFT to analyze the data rather than a swept sine is to make sure that we avoid measuring the results of any standing waves in the tank or reflections. The reflections can be not just from the sides of the tank, which even though they have an anechoic lining, there can still be some reflection, but also from the water surface, or in this case, because we have two large transducers, large diameter, the sound can be reflected between them. So you don't see any reflections in here, but if I increase the scale of our receiver signal, you can see here is another chirp coming in, and that is a reflection. If I change the time scale, so you can see how this chirp is repeated, what's actually happening is that this here is our drive signal. As you go across in time, you get the first received signal at the receiver, and then as you keep going, this is a reflection.